Hi. Good morning, everybody. Thank you, Sir Korsak and your team for inviting me to share with you some things about these three related topics: creativity, intelligence, the thinking, and also robotics, and how they are related to each other. So I'm a very informal person, so I hope you can feel free to interrupt me anytime, or if you want, you wait later, it's okay too, right? So I start with some questions that I wish we can think about. Do you agree with this? Life is full of problems? Yes, yes. But do you believe somebody, maybe a monk or somebody, an enlightened person, will be so satisfied in life that he thinks there's no more problem? Are there such persons? Maybe, right? But I think they have problems, they just don't know it, right? Because problems is not really now, right? Because if you think about an example, for example, in my parents' time, there are no hand phones, correct? If there are no hand phones, if I bring back maybe 50 years ago, there's no hand phone, you feel something's missing in your life, right? As I'm sure if you forget your mobile phone at home now, you will go back. And even if you don't need it, it's like you're missing something in your life, right? But if you ask your grandparents, there's no hand phone, do you think they have a problem? No, right? Why? Because you don't know what you don't know. It's kind of stupid, right? You don't know what you're missing. So they do have problems. They don't have hand phones. So the interesting about today is if we think 50 years from now, what should we be carrying, right? That somebody, maybe a future Marcelo giving a talk 50 years ago, which is now, why don't you have this gadget? Maybe we have a problem. Maybe one day, instead of carrying handphones, I'll be carrying my own robotic assistive device with me, right? The handphone is like a computer. Maybe I'm carrying something that will help me walk faster, that will help me carry heavier things. Maybe something very small, maybe. But I'm not sure. That makes it exciting. So indeed, the world is full of problems, even if you don't know it yet. And I think that is what drives us, why we live every day, we wake up. We want to think of not only current problems, wouldn't it be nice if we can do some things better, right? So what is the purpose of life? I think the purpose of life to be is solving problems. Because without problems, life will be so boring and uninteresting. And this is getting philosophical. That's a different topic altogether. But let me just briefly mention that perhaps the ultimate question in religion and maybe philosophy, if God is all powerful and nice, why is there evil in the world, right? Why is there still suffering? My simple answer to that is without evil, there won't be any happiness. Without hatred, there won't be love. Without ugliness, there won't be beauty, right? So everything is like the yin and yang. There's always two sides to it. So I think that's the purpose of life, and I think it doesn't end, right? Life keeps improving. What makes life interesting is once you reach that stage, you still want to do more and more, right? It's a moving goalpost. So that drives us, and I hope we don't only look at the problems we have today. We should ask the question, would it be nice if we could do this? Would it be nice if I want to go to the airport, I just flick my hand, I'm there in 5 minutes? Would it be nice if I go home, I don't need to turn on my computer, but maybe an AI robot will let me know, okay, this is your emails today, right? Or when I wake up, and it will do everything for me. It will only ask me for help for those sensitive questions, right? Wouldn't it be nice if we can do this? And how do we know we need something? And that is also very interesting. And that is a good example is the difference between the iPod, which is the Apple sound player, and the creative I forget what it's called, Creative Zen or something like that. It is very well known from a technical point of view that the creative product, which is a product of Singapore, was the first and has better capabilities, right? But right now, everybody uses the iPod and the iPhone, right? And it is really interesting, and that's perhaps something that Steve Jobs is very good at, to really know that we need something even before we know we need it, right? And that's really dreaming, right? And what is it to dream, right? What is it to dream? To really think of what can we have that will make life better? Not only solving current problems, but there. So I have here a short video of a Singapore TV show.
Than at home. The year is 1900, and a lot of things are different, especially the technology. Take a look around. Fresh food is kept cool in the ice box, as long as there's a block of ice in there with it. Although some prosperous houses nearby are electrified, the light here comes from gas and kerosene lamps. Rich folks have running water and toilets, but most working people wash with a pitcher and a bowl, use an outhouse in the back. To take a bath, you have to pump enough water by hand and then heat it on a coal or wood-burning stove. It's a big job, so members of the family take turns in the tub on Saturday night. There's no telephone to get the latest news, but there is one at the general store, along with the daily paper. Full of incredible stories about new inventions. Why, there's even a story here about two brothers who say they've built a flying machine.
So there are a few inventions then in 1900s that we take for granted today. One is keeping things cool, right? The refrigerator, hot water, and flying, right? Now, how were these invented? Let's just take one example of the refrigerator or the air conditioner, right? How does it work? Now, if we look at observations in daily life, we know if I boil water, the water becomes what? It vaporizes into gas. What is that gas called? Steam, right? So you input heat energy, it becomes steam. Now, if I can find a liquid that will boil in room temperature, what happens? That means it absorbs heat from the environment and it becomes gas. And that's just a material, and that's called a refrigerant. Before, it's Freon, but they say it's environmentally unfriendly. Now they have a different material. So engineers thought of this scientific phenomena, very simple scientific phenomena. You boil a liquid, it becomes gas. How can I make this useful? So I find a material that boils at room temperature, it absorbs heat, makes the room cooler. But then engineers are faced with a problem. Then you lose the gas, you lose the freon, the material. Today it's called R410A or something. I don't even know what that is. So can I capture that in a piping closed system, in a pipe system? After it evaporates, can I make it liquid again? How do you make gas liquid? What do you do with it? You high pressure, right? You compress it, right? So if it becomes gas, you use electrical energy to compress it. Then it becomes liquid. Then you pipe the liquid back to a system called an evaporator, where it evaporates again and cools the place. And that's what we have at our home, right? Our split unit air conditioner, similar to what you have here. That's called an evaporator. And in your yard, you have the compressor, the one that blows hot air. This one blows cold air. So it's really nice, right? And that's what engineers do, how we use science to make it useful to our benefit, right? And so to do that, we need to understand science, right? And to see, really, that's the first step. But that's not enough. Perhaps that's maybe why I studied engineering, because it's nice to discover things, but I want this discovery to lead something useful, right? Which is the air conditioner. How about the plane? As the same thing, right? How does a plane fly, right? Because there's something called a lift, but I guess I won't, you can study that, maybe you know about that already, but it's interesting to really look at how scientific phenomena have been used to create inventions. Now, my next question is it easier? I always ask my students, or my students always ask me, especially those doing PhD. It's so hard to do PhD these days, especially with the internet, because it's hard to do something new. You just do Google search, somebody did it already, right? Do you think it's the answer here is yes? Right? Well, I think the answer is not really yes. It's the same, right? Or maybe it's even easier today. Why it's easier today? Because of the availability of resources. When I was your age, to find out things, I have to physically walk to the library. Today, to find out things, even in your bed, you just turn on your mobile phone, do a Google search, and you find all the information, right? So because of that, maybe it's easier. Now, is the total number of inventions in the world finite, do you think? The total possibilities? Yeah. If you think about the total possibilities as the size of this room, right? And each invention is one person. Okay? Then this room can only fill maybe 100 people, 200 people, right? If it's full, then there's no more room for new inventions. Is it like that? Right? No, right? Because the size of the total inventions is not this room. It's almost like the size of the universe, right? And because it's infinite, right? The beauty of mathematics is as follows. What is infinity? It's big. What's infinity plus 100? What? Infinity. What's infinity minus 1000? Infinity, right? So the beauty about this is no matter how much you fill inventions, it's just too vast, right? So it's and why do people think it's hard to do it today sometimes? Because of the simple fact you don't know what you don't know, right? So you have to really dream about it. So having been invented, living less remains invented, the answer is no. Okay, that's really a motivation to say that you really can do it. It's not that it's easier before. Everything is the same. Maybe it's even easier now because of the internet. Now let's do an experiment again about dreaming, right? What is it to dream? Okay? Besides saying, wouldn't it be nice to do that? Let's do a little simple experiment. Let's say we are with friends in the jungle. We're just talking, having fun, right? We walk, we have a campfire waiting for food, right? It's like what for me when I go home, sometimes I talk to my wife before coming to bed, right? I lie down there, we just say, how's your day? How's your day? I tell interesting happened to you. But my problem is I sleep very fast, right? And my wife very upset at me. Next morning he said, what was my last sentence? Yeah, that's very unfair, right? I think it's unfair. But anyway, she's used to be already. So you doze off, right? You doze off. Then after you doze off, what happens? Because you run out of things to say, you doze off, and you begin to dream, right? And after you dream, you see this thing. Yeah, when you begin to dream, it should become, you see this. So what is the difference between this graphic and the previous one? Now it's hard, right? Because I didn't tell you to pay attention, right? But you have the answer. Before was square, then became circle. Why? Why did the square become... Is it physically possible? No, right? It's impossible. You know the answer I'm looking for? You laugh at it? Who cares, right? It's a dream, right? Do you rationalize your dream? You don't, right? You don't rationalize your dream. It just happens. Another difference. What's the other difference besides the square becoming a circle? The heat before, this was outside before, right? Then it went inside. Why? What? It's a dream, right? She's polite. My proper answer is who cares? Yeah. And then after that, in other words, when your mind is asleep, right? The mind doesn't really sleep. Because if you can turn off your brain, you die, right? But the mind is so busy processing sound, all our five senses, walking, doing things. But when you're sleeping, all these things shut down. So your mind has spare capacity. So somehow it makes connections, random connections, right? From where? from observations in life, your daily life, right? It makes. That's why our parents tell us don't watch horror movies. You'll have nightmares. And I'm sure you've experienced sometimes you are solving a very difficult mathematical problem or science problem. You cannot solve it. You get tired. You sleep. Then next morning you immediately know the answer. Have you experienced that? Yes, and somehow you dreamed of it, right? Why? Because the brain has extra capacity subconsciously to make meaningful connections. So what's the moral of the story, right? Is to dream more. But if you dream more, you need to have a lot of ingredients. Dreaming is like cooking. If you're cooking with few ingredients, the chance of making a good dish is low. But if you have a lot of ingredients, it's higher, right? And where does the ingredients come from? From daily observations in life. So you have to do things differently, right? For example, when you get home, don't take the same way. Purposely get lost, right? Or do crazy things. Like sometimes I read an article called mental aerobics. Normally when we comb our hair, I use the right hand. Why don't you use the left hand? Right? Things like this. And finally, hopefully, if you do this, you will realize your dream. I just shared with you how the steam engine was invented. Okay, somebody thought if I can burn wood inside some compartment, that heat can turn water into steam, and that steam can push a piston, a reciprocating engine that will make the wheels turn. So the square is the wheels, right? So that's how the steam engine was invented by James Watt. Do you believe me? I hope not. It's my dream also, right? Yeah, but this realization of the dream is the making the good dish, right? So you have to do things differently and to get a lot of ingredients. Yeah? There are many things that are very interesting in life. Huh? I'll show you one example. Sorry. To make sure you wake up, put your hands like this. You don't need to stand up. Can you do this? Other way? No problem, right? But try changing the direction only one arm. You feel the resistance? Yeah? Why is that? Why? It's interesting because that resistance means our brain is somehow biased, programmed to do that. So we have to remove that bias. All right, remove that bias. Now, if you look at how to remove the bias is just to practice and practice like that. And that exercise some parts of your brain. There are many things on the internet you can do for exercising this. My favorite one, I didn't have time to show it. Even at your age, you can look for it. Just do a search for dancing girls. Yeah, and you will see an animation of a ballet dancer, whether it's dancing clockwise or counterclockwise. Now, if you look at it, some people can see clockwise dancing more than counterclockwise. Some can see the other way around, right? Now, the trick is, or the exercise is, you must be able to program your brain to be able to see both. Now I want to see clockwise. Can I see clockwise? Is that counterclockwise? I should have brought it here, but maybe I don't have much time. But look for it. Dancing Girls, you'll see it. Dancing Girls Puzzle. It says that when you see clockwise, it uses your right brain. When you see counterclockwise, it uses your left brain. When you do a Google search, Dancing Girls, you see many other things, of course. Yeah, but you look for this puzzle. Okay, so observations and thinking. I want to talk about learning now. Experience is the best way to learn because experience, you observe things. You not only look, you do things differently. Like you go home in a different route, you comb your hair using your left hand, you do this exercise, right? And it's not only observation but experiencing, right? Living it and witnessing it. You have to really be immersed in it, right? And to excite the senses. And Aristotle said this, It's very, really true. And this has an impact in education, right? And I'm very happy or delighted to learn that PIM is doing this kind of education where you have one semester's teaching, one semester's work, and alternating this way. Because the old education paradigm, I learn before I do. Learn to do. But perhaps the better one or new one is do to learn, right? And that's really what it is, right? I don't want to learn the theory first before doing it. I just do it. But the fact I'm doing it, I'm learning it, right? So it's really interesting. And we're trying to also do that. I'm not saying that is better than both, but we need to have both elements, right? The typical, these two ways of learning, learn to do to learn, is an analogy to something, how we do things in life too, how we create inventions, right? Like the refrigerator example, air conditioner is this, right? We understand that heat creates gas, the physical phenomena is boiling, and that's how our world behaves. Then we can control the world from the mathematical model relating input and output using an equation such as this: y is function of x. Correct. So because of this, we need to know how the science works and use that to make the world behave like what we want it to be. To make the room cooler, how can we do this, right? This is one way we do it. But another approach, I say it's an analogy, there's always two sides, like learn to do. This is like learn to do. What is the do to learn, right? The do to learn is learning from experience. Because do to learn means you have to do it first. Do it first means you experience, right? Then you learn, right? We learn from observations, relationships, and we recognize patterns and classes, and we create models, but not from physics or science, models from data, right? Data models. And from here, perhaps the question is, do we really need to know scientific and physical models to do that? Perhaps the answer is no. But if you have the science of doing that, why not, right? Right? There are many things we do that is very hard to create a learn to do. Easier do to learn, like for example, walking. How do you teach a robot how to walk or a machine how to walk like this, right? If you want the previous model, you need to have a science of a physical model of the human body, all the muscles, what inputs to the muscles will create the outputs, the motion, so I can walk properly without falling. And that's very hard. Roboticists, scientists have done that for ages, and it's still not perfect, right? But humans can walk, right? We walk. Do we have scientific models? No, because to have scientific models, you need to know the mass of each of the links, the center of gravity. It's a very technical thing. I can walk. I don't even know how heavy I am, right? Right? So we learn from experience. Maybe when I'm 1 year old, I don't even know what's the youngest age you can walk. Maybe 1 or 2, right? But then you fall down, then you learn, right? So you create a data model. If you do this, this is what happens. If you do that, this is what happens, right? So this is another way, learn or do. So you learn how to do it. Then you create the models for doing that. Recently, this approach has a new name. It's called deep learning. It's a branch of AI, of machine learning. AI is a very big term, right? Under that, there's machine learning. To me, it's the same, right? Because the fact is artificial, that means it's not alive. That means it's machine intelligence, right? Yeah. And deep learning is a kind of machine intelligence. And why it became so popular, and I'll give you another example in this, which is the recognizing patterns and classes. If you're your parent, right, or if you have a sibling who's a baby, a toddler, how do you teach the toddler that in life there are two kinds of people? One is a female, one is a male. Can you create a scientific model for that? And people have done that. There's some research on face recognition, right? Extracting the face into features. Features means the size of the eyes, number of eyes, the size of the eyebrow, the size of the lips, the shape of the nose, the complexion. Actually, there is about 30 or 40 features. Now, the value of these features combined together, right, maybe can be grouped into two classes. One class is a female, one class is a male. Now, do you think that will work? Maybe, but it doesn't work because the problem you show a face of a dog, it may say it's a male or female, right? Because how do humans learn how to do that? We don't create models like this, right? We just learn from this because the parents said like this. Even if nobody tell you this is a male or female, I'm 100% sure from induction, right? A toddler, a baby, sees people, he can classify that there are two kinds. I don't know what that is called. That is class A, that is class B. And if he sees an animal dog, that is class C, right? And the label is artificial. We create it ourselves, right? So deep learning is about understanding classes and teaching them with labels, right? And training them. Now, it became so popular recently because of availability of data. Now, the availability of data and availability of computing power. Now, all of us have Google accounts, right? Now, in Google accounts, how come we can do, why does Google give us free accounts? Because all our photos are there, all our data are there, and there's some deep learning running on this. And today's computers are very fast, especially as one good hardware company is NVIDIA. They make graphics card meant for gaming. But the usefulness of that for deep learning is that graphics card has many CPUs or cores, right? There's typically 3,000, 4,000, 5,000 cores. So you can do a lot of fast processing, right? So because of these two advances, the very tough problem in robotics or intelligence is now beginning to be possible to be solved, right? With not using science, but using learning from data. All you need to say is, this is one class, this is another class. You just like that, and you just tell it this is male, this is female. So if you want to learn about deep learning, the first application is pattern recognition, and the first examples is recognizing a cat and a dog, how distinguished, or recognizing the digits 0 to 9, right? And there are many resources in the internet that gives you all the images, all possible dogs and all possible cats. And there's even a database of everyday things like table, chopstick, fan, shoes, that you show a picture, you know it's a shoe, right? Or some things like this. But remember, you don't need to tell it is a shoe. It just classifies the object into different classes. But then, because of life, we as humans label it ourselves. This is this class. Let's just call it a shoe. Artificial intelligence is really linking these four critical elements, right? First, you have to sense the environment using sensors to know what's happening. You have to process it and to create some meaning. For example, if you have a camera here, it sees this environment. So what, right? What does that picture image mean? Processing means I want to know, for example, how many people are here. For example, or better still, how many male or female are here. Better still, how many of them are sitting down? How many are standing up? Or how many of you are sleeping? How many of you are not sleeping? Right? Things like that to create meaning. And situational awareness means this image, it means somebody is sharing in a talk here. Right? It's like a classroom environment, things like that. So it's very complicated. We have sensors already. And one of the nice things about the sensors today is it becomes so easily available now. And I should say it's spearheaded by Microsoft when they invented the Xbox. The Xbox Kinect sensor is an off-the-shelf sensor. The Kinect allows you to do gestures. You can play tennis. You can wave your hand. You can do things, right? And because it's a consumer product, it's very nice, right? It's very easily accessible. And being in the internet, there are many people have developed software development kits, all the software available for Kinect. Right? I'm very happy when I saw the Kinect being used in one of the 7-Eleven flagship stores here. In the robot, there's a hidden Kinect there, so you can see when you're doing something, right? So that is sensing to perception. After you do that, so what, right? You have to plan your actions. What do you plan to do? And after you plan, you do it. And after you do it, you learn from how you have done it. It's something like walking too, right? Walking, you sense the floor, you walk, you plan how to walk, you fall down. And after you fall down, you learn how to walk better, how to plan your walking better, or how to sense better. Maybe from your walking, you know, this kind of floors is slippery, this kind of floors is walkable, right? One of the applications of this is a self-driving vehicle, which we are working on. Singapore is very interested in self-driving vehicle as a public transportation system. And the main motivation is to avoid traffic congestion, right? That's why Singapore is perhaps one of the fewer cities in the world we still have traffic, unfortunately, but it's not as bad as Manila or here or Jakarta, right? And if a computer is driving it, right, perhaps the traffic congestion will be more tolerable. Why? Will it remove traffic congestion? May not be, because if there are too many cars, it's always there. But if it's self-driving, you won't get irritated. Right? You can be in your car. It's like your mobile home, mobile office. You do your internet. You worry. Even jam, no problem. You can still have a meeting via Skype and things like this. But Singapore is very interested in that for public transportation. So people you don't need to buy a car, right? If I can make public transportation so convenient, nobody will own a car. Or if you do own a car, you won't drive it. You will only drive it in the weekends for recreational driving because it's fun to drive a car, right? To go maybe somewhere farther. Maybe one day I'll visit Thailand and try to go to Cambodia by car to do some sightseeing, but not for everyday commute, right? Not for everyday commute. So I was talking about that in terms of this. For self-driving car, the sensing is, how do I know this is a road? How do I know this is a sidewalk? How do I know this is where I can go? Because you don't want the car to go up the sidewalk, right? and go somewhere that's not supposed to be. So it's very interesting, right? Now, as human beings, I will remove the word intelligence because we're doing this every day. We're doing this every day subconsciously. And we don't need science to do it. But if we know science, we may perhaps do it better. Right? And this is proof that we're doing it today. I will say introduction to control. Why introduction to control? Because you are controlling how to drive a vehicle. You are controlling your motion, how to walk better. So it's really a control problem. We're doing it every day. Let's say you buy a new TV or a radio or something that emits sound or music, right? You turn it on. You hear the sound. If the sound is too loud, what do? You make it softer. But if you turn, instead of making softer, if you turn clockwise, it becomes louder. So what do? You turn counterclockwise. I experience this every day. Right now, this morning, in our hotel room, for hot and cold water, there's red and blue. I would think go red will be hotter, right? But actually, it's the other way around. So how do? You just do it. If it doesn't work, you do it the other way, right? So you hear the sound, decide, you turn that up, and you keep doing this, right? And how fast you do it depends on how intelligent you are? No. Maybe yes, but it's really how excited you are. Yeah, if you're an old person, maybe slowly. It's almost like driving a car, right? It's the difference between somebody who just got a driver's license, very excited, or your grandfather, grandmother driving a car, walking slowly. So it's really the control frequency. We do it. Now, this very simple task, how can you let a computer do it? Well, you can do it. You have to put it into equations. Desired sound level, the actual sound, and the setting of the knob, let's say -1 to 1. -1 is the lowest in one side, 1 is highest in the other side, and you create a function, which is your decision, your control action. And this can be, for example, a function of the difference between SD and S, right? And what's the difference between SD and S? The bigger SD and S difference, the bigger the U, for example. So it can be as simple as U equal K times a constant times SD minus S. Will that work? If we turn the knob. If the knob is the correct setting, the sound is at the correct sound level, what do? Do you still turn the knob? You maintain it, right? So when SD equal S, U is equal to what? 0. So it's wrong, right? So that tells me, man, so it's not U equal SD minus S times K, it's delta U. How much delta U is? So you change the equation, delta U is K times SD minus S. Then your U is your old U plus delta U. So if before its setting is at 5, your delta U is 0, you don't change 5 anymore, right? So that's what we're doing using common sense thinking. So we're doing it, unfortunately, we have to put it in equations because you need a computer to do it. Yeah, you cannot just tell a computer to do it, so you have to put it there. Another way to do it is, I don't want to even think of this U equal U plus KD SD minus S. Maybe I just learn from the data, right? At this knob, this is the sound. At this knob, this is that sound. So from this, I know what should the sound be. So that's also possible. That's the two approaches, one doing science, common sense, one using deep learning. And the question is, do we really do this in our everyday actions? Perhaps more so no, because most of the time we learn from experience. So in robotics, we try to use AI to make robots better by learning how humans learn. And what's the starting point? The starting point is, how do humans learn? That's very hard to answer. Psychologists try to answer that. Medical people try to answer that. Behavioral people try to answer that. But perhaps the simplest is studying the brain, right? How does the brain work? So this is a very primitive approximation of the brain. This is one brain cell, another brain cell. The human brain, I don't know how many millions or maybe billions of cells connected to each other, connected using this axon, right? And each cell receives signals from many other cells going to it. Here I just show two cells in one connection. Now, the key is, depending on how many signals this cell receives, it will send another signal out, right? In other words, how excited it is this neuron. Imagine all the other neurons send signals to it, but if all the other neurons are lazy, right, this will also be lazy, right? But if all the other neurons are hyperactive, this will also be hyperactive. So somehow, by this combination of cells doing this hyperactive, no problem, thank you. Using these cells, something hyperactive, something not hyperactive, it can do some marvelous thing, right? So we try to copy that by having a summer that accepts signals from many other cells or neurons. And depending on the output, this is very active, this is sleeping. So it can be dormant or it can be hyperactive. So here I show only 0 or 1, but in reality, it can be half active, 1/4 active, so it can be an S-shaped curve rather than a z, or a step curve, right? And we can have a mathematical equation for that. A mathematical equation for that is what people call, for example, is a sigmoid function or hyperbolic tangent function. It has, or pretty much any curve that looks like that. Yeah. And then there should be a teacher learning from experience that shows how much activation is happening, how much weighting is done, and that creates the output. So if we can have a massive amount of neural networks like this, a network of neurons, perhaps it can start doing things like how our brain works, right? To do things like recognizing a dog from a cat, recognizing how to walk, and things like this. It's not new. It was first invented by Bernard Widor in 1960 in Stanford. And in the 80s, McCollum and Pitts created the multi-layer adaptive linear element. And it's very exciting. I remember because I joined Singapore in 1989. That was one of my first projects, a neural network. But during that time, there was a lot of interest, but the computing power is very slow, right? And we are programming using the IBM PC, right? The PC running DOS. The data, we need massive amounts of data. It's not easily available. We created our own simulation data, right? 1989, there's no much internet in Asia at that time. I remember when I moved to Singapore, I have problems finding computers that can read my data, yeah, that I did for my PhD work. So because of that, it sort of died down, right? It's something like a lot of hype, then it died down. And only in the late 1990s, it was 10 years sleeping after that. Then in the early 2000s, when the internet came and all the NVIDIA graphics card came, and there's a lot more work. And at that time, in 1989, 1990, we're looking at 3 layers network, where the first layer is maybe 2 inputs, then 10 hidden layer, one hidden layer with 10 neurons, and maybe 2 outputs, so looking at about 15 neurons. But today, we're talking about hundreds of layers, where each layer is hundreds of neurons, and sometimes even thousands of them. Right, so because of that, it became very active again, and the availability of data was there. Right? So we put them like this. This is 1 layer, 1 layer, 1 layer, and there are many algorithms in the internet that you can download that can do this for you already. You don't need even to program. All you need is to show it data, right? The input and output data, and a teacher. The teacher is you, because the data, you have to label them. For example, if you want to detect a dog from a cat, you need to have 1 million pictures, not million, maybe thousands of pictures, and somebody has to say these are dogs and these are cats. And just give it to the computer. The computer will solve this, right? You decide how many layers there are, how many neurons there are, and it will solve what are the shape of this, what should be the weights here that will create a good approximation. We can achieve about 95, 99% accuracy now, but not 100%, right? Why not 100%? Because this is, I don't know the answer to that, but maybe my closest answer to that, this is based on how the brain works, right? Are humans perfect? No, right? So maybe because we try to copy the brain, maybe that's why too. Right? So there are many tools available, so please use them. They're free, right? All you need is a training data. You decide how many layers. How do you decide how many layers, how many neurons? You do trial and error, right? If this layer architecture gives you 80% error, you try make it bigger, and 90%, 99%, but you won't get 100%, right? So how to use a computer, right? There's input, go to a computer, and there's output that happens, right? The computer is really operating in the digital world, but the world around us is analog, right? Digital means it knows only 2 states, on or off, or true or false. But our world is analog, so you need to convert analog signals into digital, right? And for example, an 8-bit digital word is this, right? 8 bits because there are 8 of them, and each bit has a possibility of 0 or 1. And you have to convert them to, for example, the analog equivalent can be this, can be the lowest value, this can be the highest value, right? And you just do a simple interpolation. So even if the world is analog, right, it doesn't mean the computer cannot do that. Huh? You can always approximate an analog value using a word consisting of digital bits, right? But the world is not only analog, it can also be digital. The world can also have on-off. Like, for example, the lights, are the lights on and off? So that's easy. But you want to know the temperature of this room using a computer. So the temperature, let's say, is 24 degrees centigrade. And the minimum may be 20, maximum may be 40. So you have to create a digital word to approximate that, to discretize the world, right? And if you want it to be more accurate, you create more bits, right? That is why computers that require more accuracy, you need a 32-bit, 64-bit, right, to represent more accuracy, more accurately the analog values. Okay, so you have a representation. This is the first, remember the 4 things? Sensing, right? You sense the world, temperature or on-off switch. Then you have to do some thinking. The computer thinks, and after the computer thinks, it needs to do some actions. The third, right? And the actions, you have to always convert it to analog world or digital world too. Because, for example, if it's too dark, you turn on the switch. So that's digital. If it's too hot, you increase the power of the air conditioner. That's analog, how much to increase the power, right? So you always need to do this. Sense, think, act. And this is happening. Sense, think, act, every time, right? Read the sensor, you think, and you output, you do something. And this happens in a computer at a certain frequency. For machines, we're talking about 1,000 hertz. It's typically 1,000 hertz. That means every 1 millisecond you have to do this. Of course, the faster you do this, the better. For example, driving a car. If a robot is driving a car, it reads the sensor, see what the environment is, it thinks what to do, and it steps on the accelerator or turn the steering wheel. How fast do we do this as human beings? We're not digital, right? We do it continuously. But still, continuously, it's not really continuous. You know why? Our vision system is easily fooled. Have you seen a wheel, a tire turning, or your electric fan? Depending on the speed it turns, sometimes it turns the other way around, right? Do you experience that? That's called aliasing. That proves that our eyes is sampling at a certain frequency, and depending on that frequency of that tire moving, the signals you think can be alias, can be a fake. It's like fake news, right? It tells you something else. So for that, you need to sample at a different frequency, right? So we have to do this on a computer, and that's called a real-time process. Real-time process means doing each one in the actual time, right? In the real time. Many people confuse real-time process to be fast. Real-time process doesn't mean really fast, right? It just means real time. If I want this every 1 millisecond, at every 1 millisecond, I want to be able to do these 3 things. After 1 millisecond, another 3 things all the time, right? Unfortunately, Windows is not real time, because if you're doing this as a process in Windows, let's say as you're doing this, somebody tries to open an Excel file or runs Outlook. Because of that, it will slow down. So some of these ticks may not even happen. It skips it. That means, depending on how busy the processor is, it may do only a few of them. Now, in a robot, can you afford that? Cannot, right? It's kind of scary to have a robot saying that, oh, at this time, I'm busy, I cannot control the machine. Because somebody is playing a game in the computer, right? So cannot be, right? Yeah, because a computer is always like this, no matter what. There are only many processes happening, right? It does everything in a sequence. It cannot you cannot do process one, process two simultaneously. It's impossible. Right? So what happens in an operating system? It does this, does this. After this, it goes like this. A typical round-robin scheduling. Right? So this cannot work on a real-time system. A real-time system, if one process is real-time, it still has to be here, but there must be a separate timer, right? Like this figure, right? A timer that doesn't depend on the CPU. It's like a clock. So once that tick happens, this tick happens, it interrupts all the other processes and let this do it. So that's the real-time OS. And you can buy real-time additions to make Windows real-time. If you run Linux, right, it's also non-real-time, but there are additional things you then run real-time. The beauty of the earlier computers is not Windows, it's DOS. In DOS, there's only one process running. So that's real time, right? Because and we link it to a clock. But with Windows, it's become harder already. But you can still run DOS on your PCs now and have a very cheap real time system. So the computer here, you want the computer to do something, it only sends signals. Now the signals are only information. They're not power, right? The signal is like a big on-off switch. For example, turn on the lights, and the power is from the light, the power source, your electricity plug. This one means get all the power, put it to the light. Or you can have a signal that's not binary, that's not digital. It can be half power, 2 power. So in other words, this amplifier or driver called, there's a power, there's a signal. If the signal is 0, don't give power. If the signal is very high, you give a high power. So something like this. Right? If the signal is very negatively high, you give a negatively power. So it's something like a switch, but a fancy switch. I'm sure you've seen in your homes those light switches that are not on-off only, the dimmers. The more you turn, the brighter it is. So the computer is sending a signal to see how much that knob is being turned to regulate the power. But the power is coming from the power source here, not from here. The common mistake, sometimes you use this to drive the machine. And what happens? This thing blows up, yeah? Because this doesn't have enough power to drive it. It needs to do this. So in any intelligent machine, like a washing machine, for example, that's a fancy washing machine. I think there's a product that uses what they call fuzzy logic controller washing machine, right? If you open any machine, you should be able to isolate the electrical signals that are here, doing the power, and the electrical signals that are here, doing the computing, right? And they're separated. And sometimes they're separated using optical switches, optics to send this. Why optics? Because there's no electrical connection. It's super safe, right? So even if there's some shorts here, it doesn't burn here, shorts here, it doesn't burn there. It's interesting. How does a fuzzy logic washing machine work? Forget the word fuzzy logic. How about the intelligent washing machine work? How do you make a washing machine more intelligent? An intelligent washing machine should wash clothes harder if the clothes are dirtier. Correct? Right? So given that, how do I invent a machine that will wash clothes harder? That means if the clothes is dirtier, it should put more detergent and maybe tumble more, or maybe the way you tumble, to make it tangle-free, all these fancy things, right? But the question is, then you think, how do I know whether the clothes are dirty or not? What do you think? Anybody? How? If you're washing your clothes, how do you know if it's dirty? You look at it and see what? See the dirty, right? Or you look at the water. If the water is brown, if it's white, or not white, there can be white, right? And maybe it's translucent. So then people think maybe I can just give a sensor that shines a light through the water, and on the other end is the receiver of the light. If the water is fully transparent, 100% of the light goes through, right? If it's really black, nothing goes through. So you can have an analog value between 0 and 1, black or white, to indicate that how dirty the clothes are. So these are the things you can start thinking of in everyday machines, and based on that, you decide what you want to do, right? And you do things like this, right? You sense the clothes, you do something, and perhaps if you can have a new washing machine, after it does that, then the human comes in and say, it's not clean enough. So the human input allows it to learn. So next time it does this, it will be better. In a way, it's something like you have a robot cooking your food, and you eat it, not good enough. You give some feedback. Next time it cooks better, right? So that's where the learning is. Yeah. So any machine, you all do this. In a way, we're doing this every day. So the following slides give an example for a self-driving vehicle. We do this. We're doing all of this for self-driving vehicle. And why we're interested in self-driving vehicle? Because of these reasons, right? The most important is safety. This is a no-brainer, right? Because a self-driving vehicle will have sensors that sees everything. A human driver, you don't see everything. A computer controls it. Human driver, the brain controls it. The human can get sleepy, can get emotional. Computer doesn't get sleepy. It always does it. Very repeatable. A car overtakes the self-driving car, no problem. But human driver may get irritated and run after the car, right? It can be emotional, yeah? So safety is one of the most predominant reasons. Of course, when you're self-driving in traffic jam, you can use it to catch up on your email, to do work in the car. You become more productive, even if there's a jam, right? Because now the world is connected, especially with 5G coming. It's really a very interesting world, you know? Because 5G, with fast connectivity, it changes the concept of computing, right? Everything is in the cloud, right? So literally, if there's a jam, who cares, right? I'm still comfortable, right? Too old to drive, too young to drive, too much to drink. And of course, if a computer driving the car, it will drive it in the most efficient way without wasting power, not abrupt braking. And it will typically be electric vehicles, and it will be very efficient, right? It'd be so nice. I wish Singapore would use 100% electric cars. We will breathe much cleaner air. And Singapore is very ironic because it's a small country. It's really an ideal way to have electric cars. Maybe one day we'll have that. I call this the Ds in robotics. These are dangerous tasks, degrading, demeaning, dirty tasks, 4 Ds. And the closest, most interesting D to me is driving, driving vehicles. Because I think these are applications that machines can do better, one. And second is applications that humans don't find it to be meaningful to do. It's kind of boring to drive all day, right? Or boring to be cleaning toilets. It's a dirty task, cleaning the floor, cleaning. So these are candidate applications for robotics. So our work in self-driving vehicles is meant for the road and pedestrian environment. This is our university in Singapore. Engineering is here. My office is in E1. Our Advanced Robotics Center is here. Let's say I want to go to the nearest train station, and I don't want to walk, right? And it's too far to walk anyway. So I take a car from here to here, right? From here to here, but a car cannot go like that, right? Maybe a small scooter can do it, a small personal mobility device, or a golf buggy can go from here to here. Then by the time it's here, then on the road, I'll get a car that will bring me to the train station. So that's our concept. Can we have a car on demand or mobility on demand service? And these are the vehicles that we have. These three are meant for non-road environments or pedestrian environments. This is meant for a usual car for the road environment. And we call it multi-class mobility on demand. The concept is you book the car using an application on your phone or web, as long as you have web access. This car is named DJ. It's called Driverless Jockey. It's also Damon Jie, one of my first students. All our cars are named after my first students who work on that car. So it comes to you. This is one of our buildings in our campus. And the car moves. And you want to go to the train station. But then, in a typical university campus, it's big, many buildings. You cannot, it's kind of hard to walk from end to end. So you take this vehicle. So it walks in a pedestrian environment. There are no other cars there. It goes through buildings. One unique thing in our work is we do not use GPS, right? Because GPS is not available indoors. Right? Most of the people for cars like Google, Uber, and Waymo, they all use GPS. We don't. That's our canteen. And by the time it goes to my other student, Scott, also means shared computer-operated transport. It's already waiting because you book it. You book the two kinds of vehicle seamlessly. You don't book twice, only once. I want to go to the Kentridge train station. It says take this car first. By the time you reach there, another car will be waiting for you. And by the time you reach there, you can see the interface. It's similar to your booking application for a taxi. Then it just drives itself. This is what the sensor sees. This is what the robot, the car is. This is how much look ahead it's looking. Black means sidewalk. This is the road. You can also see the road markings. So it needs to learn this is a road, this is traversable, this is one way. So in all our work, we don't build a car. We buy a car. We buy a scooter. We buy a buggy. And we just add sensors, add a computer, and do the programming. The three things are sensing, planning, execution, and learning. And in Singapore, in starting 2015, the government has allowed self-driving vehicles in the One North area, which is like our science park area, and this is our university. Every 3 months, we give a report to the Land Transport Authority of Singapore, the regulators, to see our experience. If they're comfortable, they will expand. So they expanded twice to 12-kilometer route, now to 55. We're very excited because now, last year, NUS is now officially part of the allowed route. Before, we are sort of doing it illegally in a way, yeah. But it's now officially. And also this, right? 9 vehicles at that time were testing here. This is our vehicle. Newtonomy is a startup company that came from our group, right? They have 6 vehicles. 8 people from some of them you saw in the video. They were the pioneer employees of Newtonomy. They're now in One North. They grew from 8 people to now about 120 or 130 people in Singapore. So I'm very excited because Delphi is another company bought Newtonomy last year, October last year, for US $450 million. So I'm very happy with my students.
Can I have questions?
Yeah, please ask anytime.
If this car
Yes,
hits somebody on the street,
yes,
who responsible for this person?
yes.
The owner of the car or the
Today,
owner, yeah.
Today, that's very simple answer, but it's a very good question. Today, there's a safety driver there. So the safety driver still is responsible. Today.
ไม่ใช่คนนั่ง not
That-
not
today.
the one that drive the car, right?
No, he's a safety driver. He's reading newspapers there. But he's prepared to take over. The regulation is they must be able to take over immediately. And I don't agree with that. Because if I'm reading the newspaper, doing something, watching movie, then the car says, take over. Then maybe I'll panic. Then it will become worse, right? And studies have shown, I've read papers, studies, humans need 30 seconds to compose and properly take over. So what? But right now like that. But that's an important question because Singapore will work towards there's no need for safety driver. Then that question becomes important, right? And the answer is it's up to the lawyers, the regulators, right, to see because it's not so different from today. Let's say a car has an accident. I'm the driver. The driver first to blame, right? But maybe I can say because I hit the brake, it didn't brake. So you blame the car manufacturer, right? And the court case has to investigate. So the same way safety driver, the first is the software company who develop the software. But software company may blame the car company too. Yeah. So, but the good thing is if it's an autonomous car, it has a very good black box. It sees everything. It's almost like a car today with the dashboard camera. It's very interesting now to if you have accident, it's very easy to say who's to blame, right? But the autonomous vehicle would not only have that, the speed, it has everything, right? It has everything. Yeah. So, yeah.
Is there any case like this in Singapore?
Well, there is. Autonomy had the first accident, but no human, no human, nobody got hurt. Yeah, and accidents is bound to happen. But it's an important question. Yeah. So thank you. So these are some videos of One North.
Hi, I'm Scott.
Hi, I'm Pat.
That's Scott and Hans. They're both working in autonomy.
Delta NUS. You're smart. I'll be acting as a safety driver, which means the car will be doing the
safety
braking,
driver.
steering, throttle, everything by itself.
And the safety
but I'm
driver
just
now
here
need
in
to have a
case
driver's
of any
license.
emergency, I can flip a switch and take over
But
control.
very soon we will have no safety driver. In some states in California, no, in United States, like in California, I think they already allowed no safety driver, or the safety driver can be outside the car, but there's still a safety driver. So many of our videos are in the YouTube, so you can just look for driverless car Singapore. So I'll skip. I'll skip here because I want to show you more videos. Yeah, these are some of the problems we're having, like a lot of road construction. Singapore, every day there's some road construction somewhere, always. So how does the car know? Because we don't use GPS, we have to learn the environment. When we learn the environment, if there are changes in the environment, how do we know that it's the same environment? Humans know that very well. Even if you put a new thing there, I know it's the same place, right? But robots are not so good in that. Overtaking is a tough problem. We cannot do that so well, right? Especially if the car needs to overtake an illegally parked car and going to the other side of the road. Because government regulation says AVs should not violate traffic rules. But we know that's impossible, right? Human drivers, if I'm a human driver, I'm here, obviously I'll go here, right? I won't stupidly wait here, right? Yeah. So the question is, how much violation you will allow? This is, we don't know the answer yet, yeah? So that's how the view from the car. So that's safety driver ready to take over. You see the hand. Rain is very hard to do. The sensor, one of the main important sensor is LiDAR. It's almost like a Kinect, but a LiDAR. But it doesn't work on rain. This is the maximum rain it can work. But this is a simulator. It's not a real rain. Singapore has strong rain. So my students are having fun. They also put the wiper, but you don't need the wiper because there's no human. This is how we do mapping because we don't use GPS. So that means we have to map the place first beforehand. We can achieve about CM level. That means we drive the car manually, and the sensor remembers everything. It's something like your friend. First time you visit Singapore, you don't know anything, right? But a friend brings you around, and you remember everything. The difference is, if a friend brings you, you may forget, right? But computer doesn't forget. Yeah, so it remembers everything. And as it's remembering it, it builds a map in the head of the computer. It builds a map. This is how the road look like. And notice when it's building the map, it's adjusting. Humans do not do that because the robot knows how much it has moved, how much the map has changed depending on the motion, and it adjusts. So that's how we have tested it in our Japanese and Chinese gardens over 2 weekends before. And these some videos of that in the gardens. And the purpose is to give people a touring mode to visit the gardens in a nice way. Notice we have a steering wheel during the testing. But in the actual deployment, we took away the steering wheel. We put a monitor there. Guess where the safety driver is? We need a safety driver. Where? There's the safety driver. With a remote e-stop, emergency stop. Because they don't allow us without a safety driver.
Yeah, also because this is our very
This is from the Singapore News. We did this 4 years ago.
Alright,
Yeah, so we have better algorithms now.
right, actually slow
But
down.
it's interesting to get feedback from residents. This is doing some sort of prediction. If this crazy guy is not gonna move, I'm gonna move. But in case I have a wrong prediction, this is Wei Kang, my research engineer. I will move bigger in case you change your mind. Yeah? And we recently deployed it tested it in a hospital. This is in a hospital in Singapore. It will be nice. A use case will be also in the airport or hospital. Every time anybody needs a wheelchair, use your phone. Wheelchair, come to me. Then it just goes to you and you ride it. And after you finish, you just leave it anywhere. It will go find its next customer by itself and will do self-charging. So we're confident in a crowded environment, it should work quite well. The next slide is trying to understand a little bit on understanding the environment better, right? On how to detect objects as the robot is moving in an indoor environment. Before was all outdoor. Here is indoor. The environment, you don't have roads here, but you have desk, chair, this is using deep learning. We don't have any method to do that, to do science for that. We just show it enough desks, enough chairs, then it should be able to learn how to, which are the chairs, right? Let me fast forward a bit. This is also learning the environment. In other words, instead of learning the objects, can I know this is a corridor, this is an office area, this is a pantry, this is a lift lobby, using different colors. Yeah. In other words, how does the robot know I have changed the environment? For example, here in a classroom, right, or in a seminar room, if I go out, that's no longer a room, right? And I use different colors to describe different things. Now, humans learn, right, by giving a lifetime of data, right? But that's too slow, right? Before a person can learn how to drive, it takes years maybe. Can we speed it up? And I think the answer is yes, using simulation. And simulation allows us to create an artificial world. This is from NVIDIA in the GPU conference, technology conference in California recently. This looks real video, right? This is not video. This is simulation. Because NVIDIA is very good in gaming. Yeah, even if you play games, right? You get realistic. So this is the front. This is the left rear view mirror, right rear view mirror. the right side mirror, left side mirror, rear view mirror. So if we can create a world like this in a simulation, it's like Second Life. Then we can put our robot there, and it can learn, and we can fast forward. In other words, 10 years of life can be sped up to maybe 1 hour. And the other advantage is, since it's a computer learning, once you learn that, you can transfer the learning to another computer. We cannot do that if I let my son learn how to drive, and I want to teach another person. I have to teach again, right? I cannot transfer the brain of my son to the. But in a computer, you can do that. So the importance of simulation is very interesting, right? Can we create really a simulated world? And because it's simulation, we can create scenarios, all possible things that will happen. In a way, we are like behaving like gods, right? How will the autonomous car or robot behave in different situations? So robotics is not only about intelligence so far. No? It's also about physical objects, physical robots, right? Actions are controlled according to our own designs and with artificial intelligence. So the rest of the slide shows the robots for everyday environments, for work, home, and play, and in human environments. And the real challenge of robotics is really how to make these robots from factories to everyday life, to bring it out of the factory. This is the original industrial robot. This is a Kuka Aiwa. It's also in your university in PIM. And this is another two-handed robot. So the challenge is how to make robots go out from here in cages to those without cages. To, for example, in your 7-Eleven stores, in your groceries, in your shopping mall, in the airport, in the hospitals. So in unstructured environments where there's human-robot interaction instead of separation, right? So that's the real challenge. And AI is very important indeed. And we need to work on robots adapting to spaces designed for humans. So I don't want to change the world based on the robot. That's why we don't use GPS. I don't want to put lane markings on the floor. The robot needs to be able to operate without changing the environment. This is perhaps one of the most advanced robots in the world in terms of physical body from Boston Dynamics. This is this company is from Mark Raybert. He's an MIT professor, one of the most successful in terms of technology, but whether they're successful commercially is a different question. Yeah, it's very agile. It can do many things. It shows how good. This is not our work. This is from Boston Dynamics. This is really the best robot today in terms of physical robot, and this is a step towards everyday robotics. This is all. I got this from YouTube. You just look at Boston Dynamics robots. Yeah, you can find them. Let me fast forward a bit, show you some more interesting robots. Okay, if you have a robot that can do this, it's very impressive, but does it have artificial intelligence to do tasks for us? But certainly the body can do that. But then doing the task is a different story, right? Sometimes they call it a parkour robot. Some parkour. So we need really a physical body that's this agile. But this is not enough. I will skip this now. You can look at it more. And we're looking at really, when I say everyday robotics, we want to have robots as tools for human beings, right? Tools. They don't replace humans. But if you have this, a tool can only operate with a human. A human uses a tool, right? And in human environments, the compelling applications is the 5Ds I talked about. This is some of our work in NUS in Singapore, where we work on soft robots. So if we can combine the agility of the Boston Dynamics robot with the softness of robots, then it becomes more appealing, right? Can we have robots made of air like this? This is silicon. By pumping air, it becomes like a snake or a curly finger, or this like this, or like this, so using air. We have also used that to create a fish robot, something like this. Sorry. It went a little bit far. What happened to it? It seems to be moving by itself. Okay, here. This is another kind of robot. I'll go back to the fish robot later. This is a double-sided tape. Yeah. Again, the physical interesting thing about this double-sided tape is if you put power, it shrinks. And by shrinking in thickness, it expands. Turn off, then it contracts. So it reminds us of artificial muscle, right? Artificial muscle. So can we do that? And the same device can be used as an energy harvesting device. If you put mechanical energy, it generates voltage. This is something like the motor generator effect. You put electrical energy, it moves. You move it, it gives electrical energy. It's interesting. Can you imagine putting this under your shoes? As you walk, you're charging your phone. Yeah, something like this. But it doesn't have enough power yet, but it's interesting. And it's black here because we put carbon grease on the top and bottom to spread the charges. This is supposed to be a fish robot that's supposed to be running. Something like this, using soft silicon material with threads embedded in it. Yeah. Okay, I'm running out of time, so I will quickly skip this. This is another robot on the allowing mobility using model after the swivel chair. Imagine if a car can be like this, right? And you don't have problem parallel parking. You can just move sideways. Okay, I want to end very soon, but let me end with this slide, right? This is a slide on, I showed technology, but let's not forget a value system. This is a value system. It's almost like ethics, right? There are 2 points. One is a knowledge-based economy, right? We need to have, as academics or researchers, it's important to be able to share knowledge. And sharing comes with the responsibility of acknowledging the creators of the knowledge. Yeah? Many of these deep learning things I showed you is all available on the internet. If you use it, all we're asking is acknowledge who contributed to it. Then on that time, with that, then we don't need to reinvent the wheels, right? You can build on top of what is available, right? So I'm very encouraging. It's very encouraging to have more open innovation through sharing. That's one, and that's what a knowledge-based economy is all about. Is collaboration and acknowledgement. And this is the cornerstone of academic integrity. Second thing in the value system is social responsibility. We don't want to end up things like this. And I'll close with this very, very weird example. Singapore is trying very hard to eliminate smoking. It's the most expensive country if you buy cigarettes, right? But if you look at smoking, I do not smoke, and I get irritated by people who smoke because I get headaches, I think, with secondhand smoke. So from a technical point of view, we can always design something, right? So that smokers are happy, non-smokers are also happy. So how do you make them both happy? You build something like this, right? In other words, you want to get smoke, right? But then what do you do with the smoke? You exhale it. So why don't you swallow all the smoke, right? Then you don't do it, yeah? And everybody is happy. But of course, you cannot do things like this because this is what happens, right? He dies, right? So there's social responsibility. It's not only about technology. And we have to really do the right thing. And there are many more examples that I don't have time. And I'll stop here. Thank you very much for your attention and patience.
Thank you very much for your amazing presentation ขอบคุณมากนะคะ